In this lesson, we'll start discussing continuous 5-axis strategies, beginning with drive surfaces. For those of you who are familiar with milling techniques, you will undoubtedly have heard the term index milling. So, for example, for a model like this, index milling would mean that you position your perspective, your construction plane, for example, this way, so you can see this reflected in the top window. You would then draw boundary curves around either the whole model or parts of it. You'd mill it out. Then you would position the model this way. Then you'd mill parts that are exposed this way. Flip it over again, and then again. So this way you would cover all 4 sides, and your model would be cut out, at least on the outside, at that point. The issue with this, of course, is that first of all, it requires manual work to position your construction planes, draw curves, and calculate multiple separate toolpaths. And moreover, as you may know from experience, any areas where the two toolpaths overlap, especially at curved angles like this, there'll be a bit of a mark where one area ends and the boundary of another one begins. No matter how calibrated or accurate your mill is, you'll still see a slight transition between these areas, which will then need to be cleaned up. And the other issue with this approach is that it really was meant for older mills that relied on either 4 axes, meaning that you have your 3 directions of movement and then a lathe, or alternative 4+1, meaning a 1 manual tilting axis that you would adjust by hand between operations. Now that we have true 5-axis mills that can move all of their 5 axes at the same time, we are able to utilize a new type of strategy called continuous 5-axis milling. And for that, neither construction planes nor curves are sufficient anymore, because we need to instruct not only an area to cut from one perspective, but from all perspectives at the same time. So to do that in Rhino and in Jewelry Cam, we use surfaces. And when constructing surfaces, they're so-called drive surfaces for milling toolpaths, we need to keep in mind that really they should be as simple as possible, because the purpose is twofold. One is to instruct which areas to mill, so everything underneath the surface will be milled, and 2, the curvature of the drive surface respective to the actual model underneath will indicate how the tool bit will be positioned. So let me demonstrate this to you by milling a part of this model using drive surfaces in JewelCam. I create a simple surface. This is actually just an extrusion drawn from the silhouette of this model, just a little bit expanded outwards, so there's a bit of excess space between the model and the drive surface, and then extrude outwards to cover a portion of this geometry. As you can see, there's no trimming going on here, there's nothing super complex. We simply need to make sure that this surface, this drive surface, covers it kind of like a box or a bag would over top of the physical model. We go to our new operation and we select drive surface. We're prompted to select our drive surface, so we'll click on this. And we need to select the machining side. The green and the red arrows generally suggest which area you're meant to be machining, and green arrows being the outward surface. And if you find that you create your extrusion or sweep or whatever, and instead you on the outside you have red arrows, you could always use the direction command to invert it. But Jewelry Cam will let you select either side, the inside or the outside. So select the outside, and then we're asked for a lead curve, which is almost always the edge of our drive surface. We can also select additional boundary curves, but in this case, we're going to keep this example simple, and we will press enter for none. And finally, we're asked if we want to keep our boundary projection direction at default of C-plane, which we will. Let's set our step at something large, like 1 millimeter, and click apply. We can now hide our drive surface temporarily. It's still registered as long as it exists in the scene. It doesn't have to be visible. And let's calculate. And here's what we see. We see that our tool bit will go around this whole model, well, the portion that was covered by a drive surface, and will make cuts that were consistent with our lead curve. So if our lead curve went this way, then the cuts will be perpendicular to it. Likewise, if we had a lead curve going this way, the cuts would be perpendicular to it that way. Now, you might be wondering why, even though our drive surface was this big, we've only cut everything here, but not here. Well, this is one of the options for drive surfaces, and that's don't trim toolpath. By default, you probably want to trim the toolpath so that it's limited and stops just at the model's edge. There's very rarely a reason to cut all this other area in the same fashion. If you truly need to do this, it would be probably best to go in with a curve or cut and curve command and cut it out much quicker by really a 2D, 3D operation afterwards. However, if you must, you could specify that you don't want it trimmed and mill it out, and then you will see that it cuts out this whole area underneath. Still, you might wonder why the lines don't fall right through. They're only going so deep. Well, once again, this is one of the options set by the drive surface, the depth below drive surface. And this is something that you do have to specify depending on your model, and it simply measures the distance from the rim of your drive surface to the lowest point in your geometry that you need to cut. So here, for example, we can see that, let's say 1.12 is sufficient to reach the bottom of the side. And right now we're at 1, so we could specify 2 and recalculate, and you will see now that we are going deeper into this model. In a sense, this is the essence of the drive surface operation. There's a few refinements that you could do, but this is the primary functions of it. You create a drive surface, and that's what you end up spending some time thinking about and figuring out. And your drive surface almost invariably ends up looking like a ribbon, a piece of cloth that surrounds your model and moves along the track that you want your milling to take. It could be like this, it could be in a spiral. As long as it's a single surface, not a poly surface, it will work as a drive surface. Now, there are a few other options to consider. First, as with some of the other operations you've seen, you have options for using additional check surfaces. For example, if you want to prevent the toolpath from falling below this area, you could create another flat surface here and specify it as an additional surface. You could change the lead curve that we specified. So instead of cutting this way, we could cut this way. And we could also change or add a boundary curve if you want to further restrict the cutting of this model. Beyond that, we also have an option to specify our tilting. By default, we're letting JewelryCam do what it needs to do to cut this in accordance to our drive surface. So let's trace the steps back for a sec, make this a little bit finer of a cut, like so, and we'll take away our don't trim option, so it is trimmed, and let's look at a simulator to see just how this model is cut. Let me speed it up a bit. So you could see that JewelryCam knows to rotate this as it cuts without doing extra moves in the areas which are unnecessary. And because this is one operation covering all the angles, there will be no seams and no connections, no steps or anything like that. It's a very, very clean way of cutting out this part. Our tilting option here is set to default, orthogonal to cut direction, meaning that it should try in as much as it can to cut from a vector that's always perpendicular to a surface for the cleanest surface possible. You can change this as well. You could set to tilt fixed to axes. For example, you could set we had at a 90-degree angle on the side by default, but we could set to say 100 degrees. And let's see how that affects our milling. Right away you'll notice that now we're tilted at 100 degrees. And so we have a slightly downward tilt on the model as it cuts. This is often useful for getting into certain tricky areas of the model, or when you want to ensure that you do not go beyond a certain tilt angle. For example, if your machine can only cut 130 and below, you could set that as a limit, cut the part out knowing that it will not cross it. You can even get more sophisticated using tilt line definitions. If you recall from our cut and curve instructions and engraving instructions, we could specify lines as vectors, meaning that at different areas of the model, we could specify which angle the tool should point at. So here, we could do the same thing. Let's say we create a few lines that specify how a tooltip should be positioned at various stages. And I'm choosing it somewhat arbitrarily. Let's say there's 3 of them. We set the snapping distance. This is important because if our line's a little bit away from where they need to be, JewelryCam will have a hard time finding them. So we need to make sure that we have our snap set to accommodating distance. So I'm going to set that to 5. And for tilt lines, I'm going to specify 1, 2, and 3. And press enter. Click apply and recalculate. We get a somewhat strange diagram of our toolpaths, and that's because we're placing fairly strict constraints on how these certain toolpaths are cut as our toolpath is progressing. And as you can see, there are some areas under this definition which it's not able to reach. because now we're in a continuous 5-axis strategy. Between these curves, Jewelry Cam is trying to find the average of these two tilting angles. So it'll progress slowly from this angle to this angle, for example. Let's see how that looks and how it differs from our previous tilts. So we begin at a 90-degree angle. And we continue, but now our model, the way it was cut, looks all funky because we've placed a limit on the natural rotation of the B. However, if we took the same thing and looked at it from the perspective of the A-axis, you'll see that all of these lines are still in line, meaning that we are not tilting the A at all, we're kind of prohibiting it from tilting. Let's change it a little bit. So let's move one of these lines this way, and the other one a little bit this way. They're still the same tilting lines, but since we've changed them, we have to reselect them again. 1, 2, 3, press enter, apply, and recalculate. And now we have also introduced a tilt to A-axis. And you can see that right away, even before the milling, because our A angle is different. Well, let's proceed with the simulation anyways and see what happens. Now you can see that we're moving our A and B according to the tilt lines. This is actually a very useful function because sometimes you want a certain segment of your model to be cut in an exact direction that you have in mind. You might leave everything else at default. You might create tilt lines that are exactly perpendicular as you would with a default strategy anyways. But then for a certain angle, you might say, well, I want to cut precisely this way. And tilt line definitions allow you to do just that, while still working with the same very basic primitive looking drive surface. Finally, there are a few more options that are worthwhile discussing. There's extend or trim toolpath beyond the tool diameter, and this allows you to just exceed the border by a little bit to go slightly beyond the edge of your model, which can be quite useful. You can also reverse the lead curve direction, so that's not the same as changing its U or V direction, but rather say from going clockwise, you can go counterclockwise in this case. And you can use, instead of one lead curve, you can have a morphing or an averaging between two curves to indicate direction. So for example, if you wanted to cut this the diagonal, you could do that too. So that, in a very quick overview, is the drive surface. And drive surface strategy is probably the most powerful cutting strategy that you'll find for 5-axis mills going forward. It's just a matter of getting used to it and learning to draw drive surfaces rather than boundary curves, as you may have done with index milling before.